And this is technical or theory. This is more like the model building side of this electroweak phase transition, not so much about the phenomenology of the electroweak phase transition, which is kind of the main line of this workshop. But okay, it's still electroweak phase transition, electroweak physics. And what I'm reporting here is lattice numerical studies of these models. So the background here is that, as we all know, the Higgs field is special in the Standard Model. Firstly, because it hasn't been found, the only one which is missing. And secondly, theoretical reason, it's a scalar deal. And because it's a scalar, it in a way leads to many theoretical problems. You do have the famous hierarchy problem, I mean the fine-tuning problem. Vacuum stability issues, unitarity bound issues associated with the scalar. I don't myself consider this to be really serious deficiencies of the Higgs model. I mean, I think people nowadays accept it from the outset that Standard Model is only an effective theory, and there you can have all kind of these problems, but you know that Standard Model will be taken over by some other theory at some higher point. But for a long time people did make an issue out of these topics, problems associated with the scalar field. So the question arises that can we do without the scalar? I mean, can we have the Standard Model phenomenology without the Higgs field? And indeed, it is a priori possible. We can compare the electroweak symmetry breaking and the chiral symmetry breaking in QCD. In electroweak symmetry breaking, the condensate, the order parameter, which kind of measures the symmetry breaking. In the electroweak symmetry breaking, that's the Higgs field expectation value, and in chiral symmetry breaking, it's the chiral condensate, psi bar psi. Here, this is a local symmetry which gets broken, so they are not really Goldstone bosons, but I mean, as people usually express it, that the Goldstone bosons are eaten by W and Z modes, because it's a gauge symmetry, whereas chiral symmetry breaking is a global symmetry, and there you do have Goldstone bosons, the pi mesons. And the radial excitation, I mean the excitation of the magnitude of the order parameter, corresponds to Higgs particle in electroweak symmetry breaking, and chiral symmetry breaking is a scalar meson, sigma meson, which is very heavy. And one should also realize that the QCD symmetry breaking here does break the electroweak symmetry, as Matti mentioned, because this chiral condensate, psi bar psi is actually psi bar r psi left. So you have right and left, of course, I mean in this kind of doublet. So this left has a weak index, A, and the right doesn't have a weak index. So it looks exactly like a Higgs field or something. When this is an expectation value, you break the electroweak sector. Of course, this can be the other way around, but it doesn't matter. You still have one dangling index there. Thus, you can break the electroweak symmetry by fermion condensate too, if the fermions have an SU2 charge. And we know very well the chiral symmetry breaking, we know that it exists in QCD, we know QCD quite well, we know the dynamics of it, so why not to apply this knowledge to electroweak also and somehow the minimal approach. It has kind of symmetry and I don't know, this kind of minimalist solution. When you have one mechanism, let's reuse it in everywhere where we can. And the models where this happens are called technicolor models. So here, electroweak symmetry breaking happens to chiral symmetry breaking of TechniQCD, which is the new gauge proof TechniGauge plus those techniquarks Q. And where the lambda parameter, the scale where this happens, is now this electroweak scale. These techniquarks must have technicolor charge, of course, because that's the color group there, and the electromagnetic charge, or the weak charge. So the left-handed technique quarks coupled to the weak group, but the right-handed not, same as the normal quarks too. And after chiral symmetry breaking...
Why do you need an additional gauge group, bigger gauge group?
Why not SU3 or?
Why not just the SU2 cross U1, the electroweak gauge group?
You cannot do it with only, well, I mean, you want to have a chiral symmetry. Well, SU2 alone would have chiral symmetry breaking at ridiculously low energies, because the SU2 has a very weak coupling. So that if you would run that to strong coupling, I mean, if you assume that there's no QCD, that would have a chiral symmetry breaking, but the scale is of order electrovolt, I think, or something. That the SU2 mesons would be of, I don't know, planetary size, I have heard. Some way. It depends what kind of particles you take into account, because this is now speculating if you are not in a standard model anymore. But the SU2 doesn't undergo chiral symmetry breaking until you reach extremely low energy, so it cannot be relevant here. So you need something extra. You need QCD like, well, you need much stronger coupled theory at the relevant energy scales, and thus, I mean, you need some new gauge groups there. There are some models that where you don't have technique quarks, I mean that you use the existing quarks. I'm not expert on these kind of top condensate models, so that you, as far as I understand, they have a kind of new gauge group which couples to heavy quarks and top quarks, let's say top family, and somehow makes a top condensate, but I don't think this works. I'm not sure, but my impression is that this doesn't work. And now again, I mean, after chiral symmetry breaking, you have a meson, QQ bar, this technique quark meson, and that's your Higgs, I mean the scalar meson, the pseudoscalar mesons, which are the normal chiral symmetry Higgs, pions, chiral symmetry pions. Now, because these have also the weak charge, these pions don't exist as physical particles, but they are eaten by the WM set, so that at least 3 of them are eaten. If it depends on the symmetry, if they are more than that, then you will be left with these pions, light pseudoscalars, which are the Goldstone modes of this chiral symmetry break. And then, of course, because like in QCD you have a huge number of hadrons, in principle you have lots of exotic technihadrons in this model. So there's a spectrum of exotic particles, which is in principle, then, of course, observable in experiments. Now, this idea works very well for the Higgs gauge sector alone. If we take that in isolation, I mean, no problem. We can have electroweak symmetry breaking with SU2 cross U1, and we obtain the phenomenology what we want. However, the problems arise when we really want to match to the standard model the quark masses. The Yukawa sector is very messy in the standard model, and that leads almost unavoidably to very messy solutions in Technicolor. And this is, I think, the weak point of the Technicolor theories, of course, and breaks somehow this minimalistic solution nature of the Technicolor theories that you need to achieve the Yukawa coupling. And Yukawa couplings are not yet there, I mean, on the theory what I showed so far. I mean, if I have only these exotic technique quarks and let's say technique gluons, and these technique quarks have also SU2 charge, it just takes care of the symmetry breaking, but there are no Yukawa couplings yet, so that you wouldn't get quark masses. So you have to posit a new interaction. Again, a new interaction, and that's called extended Technicolor. It's again a new gauge interaction coupling normal quarks and technique quarks, so that it's an interaction which couples both sectors. And this happens typically at energy scales of lambda ETC, which is normally assumed to be much larger than electroweak scale or the Technicolor scale. And that is because otherwise, if they were close to each other, you would get conflict with the experimental constraints, too large flavor changing neutral currents. This is very generic feature. And the Yukawa couplings now in this theory will be, I mean, of the kind that you have this Technicolor condensate due to this Technicolor chiral symmetry breaking, and this condensate couples the quarks through effective 4 fermion coupling, where you, of course, dimensional reasons, you have this 1 over, oops, there should be lambda etc square there, of course, dimensionally. I mean, that originates really, of course, of this exchange of this etc gauge boson. And in order to avoid those flavor changing neutral currents, this lambda etc has to be quite large, typically of order 1000 times electroweak scale. So you have this factor of 1000 from electroweak scale to this 1000 electroweak scale, etc scale, where the Technicolor theory kind of you restore the chiral symmetry, and the Technicolor theory is kind of the theory which describes the physics, and then at this higher scale lambda etc you go to some new theory which can be much more complicated and actually kind of in the spirit of let's say effective theories, you can be almost anything. You don't have to specify what this etc theory is. But if you want to, of course, have a complete description, then you should have some model how it works. That's not really in my expertise. But in order to make this work in practice, you have to restrict the running of the coupling constants. The coupling constant should evolve very slowly between the scales, electroweak scale and this extended Technicolor scale. This extended, at higher scales here, you are now in some larger theory which we don't know about, but this theory gives rise to these 4 Fermi couplings between the, I mean effectively at lower energies between the Technicolors and quarks, which give me the Yukawa couplings. But now I have to push these scales apart in order to satisfy experimental constraints, and in order to have the chiral symmetry breaking not here at very high energies, but down here at lower energies, the coupling cannot run, I mean, like this, I mean, like a natural manner. I have to hold it back. Stop, don't grow yet. I mean, stay small or stay roughly constant until I get to much lower energies, and then I can go up and have chiral symmetry breaking and Higgs mechanism. So this is a mechanism somehow just to separate those two scales, the electroweak scale or the QCD scale of the Technicolor theory here, and this new, let's say, the larger theory scale, etc., where I have some new theory coming into play. And this is, of course, not very natural to have a behavior like this. But turns out it is possible to do. This implies a beta function. Beta function, the definition is just this, mu times dg over d mu. In order to have this kind of behavior, beta function looks something like this. This is the coupling constant on this axis, and the weak couplings are here. QCD, like beta function, is here. It just dies down. I mean, the larger the coupling is, the faster it evolves until it really diverges at some strong coupling region. Now, if I want to stop the evolution of the coupling, the beta function has to, of course, go close to zero. I mean, the change in the coupling when I change the energy. It has to be very close to zero. But it shouldn't go exactly to zero, because there it doesn't evolve at all. Then I would be at the fixed point. So it goes close to zero, but then again diverges from it, so that at strong coupling, this branch corresponds to this. It again kind of evolves quickly. And this branch corresponds to that, and this region is that flat region. So here you see other options for the beta function. This is the QCD, the standard asymptotically free theory. Here is your asymptotic freedom. And if this really goes through this 0, then I have a fixed point. Because at this point, if I change the energy, the coupling doesn't change. So that it's actually conformal, the theory. Coupling doesn't change when I change the scale. It's scale invariant, and it has special conformal behavior there. So if the beta function is of this form, then the coupling actually would just go, well, actually I should go from this higher energies, it would go asymptotically close to this fixed point value and stay there forever. I mean, if I go to lower and lower energies, it doesn't kind of cross over into larger values. Okay, is it possible to have this kind of beta function? You remember that in QCD the beta function looked like this. If you have no quarks, I mean it types down like that. You add quarks, it becomes larger. You add more and more quarks, I mean it tends to reduce, I mean or make it go down slower. And actually there is one number of quarks, specific number of quarks in QCD, which is around 17, 16 or 17, where this changes sign and you lose asymptotic freedom. The theory is not asymptotically free. And now when you calculate this at 2-loop level, you can have non-trivial behavior also in QCD that you have a behavior where you have a non-trivial non-zero coupling. Okay, and same thing could be in technicolor theory. Let's say SU2, you just add suitable number of quarks so that you will get a 0 here, or almost 0 at the larger values. But the required behavior is very difficult to obtain using fundamental representation for us, because then we need lots of those quarks, like in QCD 17 or something like that, 17 families, and this gives rise to very large flavor change in neutral currents. But in other representations, let's say 2-index symmetric representation quarks, very small number is sufficient. And turns out that at least according to perturbative calculations and estimates, there exists so-called conformal window where there's an infrared fixed point in these theories. So that, let's say, using a theory with 2-index symmetric quarks in SU2 or SU3, at some specific value of the number of flavors, if the number of flavors is very small, you have the normal asymptotic freedom. You increase it, you get the non-trivial 0, and then when you increase it further, you lose the asymptotic freedom completely. And it's shown in this plot, similar kind of plot what Matti showed you before. For example, if you have SU2, NC is 2 here on this line. If you have the number of flavors which is equal or larger than 3, you don't have asymptotic freedom at all. This is a exact statement because you can calculate it perturbatively. Here, one loop calculation is enough. That there is no asymptotic freedom. Now, if you have a very small number of quarks, 1 or less, you have normal confinement. I mean, you get a strong coupling at large distances, and presumably, well, you would have chiral symmetry breaking if you had more quarks. You cannot really talk about chiral symmetry breaking when you have only one quark flavor. But here in between, you get this, and this is called conformal window. It has this upper edge and lower edge. Upper edge is exactly calculable in perturbation theory. Lower edge is an estimate here, and this band kind of tells the range of these analytical estimates. And the question whether or not you do have this behavior or not is really non-perturbative. Basically, it happens. I mean, its fixed point would be fixed point is non-zero coupling, so that by definition almost, I mean, non-perturbative issues can be important, and chiral symmetric breaking especially is a non-perturbative phenomenon. So you need something non-perturbative to assess that situation. And numerical simulations have been done on SU2 with two flavors, which is actually adjoint, two adjoint quarks, adjoint representation quarks, because that's the same as this two-index symmetry for SU2, and SU3 for two-index symmetry quarks. Okay. And why we need simulations? Just because, I mentioned, chiral symmetry breaking essentially non-perturbatively, and this conformal, would-be conformal point is that could be at large coupling, so that perturbation theory is of questionable reliability. And okay, here we study two SU2 and with two massless flavors, the simplest model in this class, and this is called minimal technicolor. Commonly. And that theory has been studied by many other authors too. And this SU3 with two flavors has been studied by Degrand as well. And what we study here, firstly, we can measure particle spectrum, kind of normal lattice calculation. You measure what kind of hadronic spectrum you get, what kind of hadronic masses you do get there. And do we observe chiral symmetry breaking as in QCD? Or alternatively, do all of those particles become massless as quark mass goes to zero, which indicates no chiral symmetry breaking and possibly a conformal behavior. What we also do, which is really the central point here, is that we measure directly the evolution of the coupling constant using so-called Schrödinger functional method. I will return that later. So that the model, to repeat this, is an SU2 gauge action in fundamental representation, normal SU2 gauge action, but the fermions, which are massless, are in symmetric, two-index symmetric, sorry, it should be two-index symmetric, which equals to adjoint representation in SU2 here. So that this covariant derivative is not your normal covariant derivative, and these fermions don't have two components but three components, because the adjoint representations have three components. In SU2 you have three generators. And on the lattice, numerically, how this is implemented is that the gauge fields, which are so-called link matrices U, they are in fundamental representations 2 by 2 complex matrices. But for the fermion action, these are transformed into adjoint representation matrices V.
The covariant derivative, how do you write it?
Well, covariant derivative is just d mu is normal d mu minus I g, and then you have the normal A mu and A, which is the normal vector potential, but then you have the adjoint generator T A, where adjoint generator is actually T A B C is I F A B C. Structure constant, which for SU2 is I epsilon A B C. And so it's exactly like the fundamental, except the generator is not the normal one, but it's the adjoint representation generator. So it has really, it's a 3 by 3 matrix, not 2 by 2. And we use standard Wilson fermion action for the fermions, which is the weakness of our approach, but that's the simplest. Okay, now first some lattice technical points. This is completely standard in a lattice formalism, this stuff, but it has no kind of direct relevance to continuum physics. The theory is parameterized with two parameters, beta or beta L and kappa, where beta basically is the lattice spacing, corresponds to the lattice spacing of your theory, and kappa is a reparameterized quark mass. on a Wilson-Fermion formalism, you don't actually know the quark mass of the theory because this Wilson term destroys the chiral symmetry of the theory. So you actually have to measure the quark mass, what you put in there. Only the bare quark mass is known, but it gets additively renormalized. And that is measured by using chiral axial word identity, which is kind of established definition of quark mass in this game. It's just a relation between pseudoscalar, scalar, and pseudoscalar currents. That's a technical point. We don't have to go there. But you really have to measure the quark mass, and then you can define, I mean, using this definition, you define so-called critical line kappa c, which depends on beta, where the quark mass vanishes. This line now you define your massless theory at any given particular lattice space. And it's shown here. These two lattice parameters are here, beta, which is the kind of parameterized lattice gauge coupling or the lattice spacing, and the kappa, which is the quark mass parameter, and the kappa c line is this black line here. And the finite quark masses are then below this, so that the farther away you are from this line, the heavier your quarks are. And we want really to be here along this line. And these dots are our measured values, and this is just an interpolation between them. Here you have some funny unphysical non-continuum phases. You don't have to worry about them, but there are some
What do you mean by measured?
Sorry?
What do you mean by measured values?
These dots. Well, we measure this ratio at various quark masses or kappas here, and observe where it crosses zero, and that's then the zero quark mass there. This is measurable on the lattice. This quantity, what is here, this relation between the currents. So we don't know a priori what the quark mass is in our lattice theory. This is the problem with the Wilson quarks, Wilson representation quarks. This is purely a lattice issue, nothing to do with continuum physics. But if we want in the continuum to have massless quarks, we have to be along this line.
What is T?
Sorry? T.
The variable T.
T. I'm sorry here. Yeah, actually, this is a correlation function. There should be T here too, and T is the distance. It's actually typically measured to time direction or x0 direction, so that that T is the time separation between sink and source of your correlation. So that this is measured at different distances, and then you go to infinite distance. It's a correlation function which you measure at very long distances, and that defines your quark mass. That's an established method. Nothing kind of particular to this model. Here, effectively, the quark mass becomes negative when you cross this model. I mean, it's a funny theory that it allows that kind of.
I'm a bit ignorant about lattice. So, what is VPS and VPP?
I didn't want to write those expressions because they are so lengthy. But this is an correlation function where the source, one point you have pseudoscalar source. Pseudoscalar is like pion. Mm-hmm. You have a pion source, and at the sink you have I'm sorry. This should be a pseudoscalar pion and an axial vector source. Oh, yeah, I'm sorry. It should be an A there. Axial vector. Correlation between pseudoscalar and axial vector. And here is a correlation between two pseudoscalars. Pseudoscalar at the source and axial vector at the sink, which are separated by a distance of t. These are chiral relations, and this determines, in chiral perturbation theory, this determines this chiral quark mass, which is what is considered to be the physical quark mass. Nowadays, the one which is reported in particle data book.
So in the end, you don't want your quarks to be massless.
I want them to be massless. This is the quark mass. I have these two parameters which I can tune. I have to tune these to make this vanish, go to zero. This is the meshless theory. But I don't know a priori what I should choose. I mean, this is a two parameters, but I tune this mass to be zero, so I get the condition for this kappa, which is a function of beta, that line. And along that line the quark mass is zero. So that this is just a mechanism to tune my simulation parameters so that the quark mass goes away. So it's nothing else. I mean, so that after I have done this, it's not so simple calculation, but it's perfectly standardized nowadays. I get this line where the quark mass vanishes.
But these dots, you said are the measured paths, but
Sorry?
these dots sit on the line where the quark is massless.
This line, this thick line, yes.
So what are these red dots then?
Oh, these ones.
The mass is zero there, no?
We haven't simulated, of course, at all betas. We have done the calculation only at these betas. And this is just, I mean, by hand drawn line through this. I mean, it's a guesstimate. We are working only on these betas. So these are measurements. They have error bars there, but they are not visible. So these are the measurements where the quark mass is zero at these particular values of beta or lattice spacing. We don't actually know a priori here the relation between beta and lattice spacing. That's exactly the beta function. But this continuous line is a guesstimate through them. I mean, it obviously the right line goes somewhere there, but we don't know exactly where. But this is enough for us. This is an illustrative. I mean, the crucial point is that we know these dots here. And this is just a conjecture. You have some funny faces here. Don't worry about that, because that's a completely lattice artifact. And there actually are plenty of those funny faces which are kind of anti-ferromagnetic, whatnot. I mean, nothing to do with continuum physics. Nothing to do with continuum physics there. Lattice fermions are complicated objects, one has to say. It's very unfortunate. Okay.
So maybe to clarify, because since you are really not expert, so the main aim is to calculate beta. This is what you want to get out.
The beta function, yeah.
The beta function.
Yes.
Okay.
I'm sorry about that. This is also beta.
This
has
is
nothing to do
another
with
beta,
beta
right?
function.
This
This is different beta,
That was
but the
the
same
confusion.
symbol. But that's just, I mean, people usually call that beta. Yes. I will come to that. This is just kind of the, I mean, one of the standard things what you have to do when you are faced with a new theory. I mean, you have to kind of map out the phase diagram and what kind of phenomenology you have, and then you can start doing kind of the calculations really with it. These points are analytically known. I mean, when beta goes to zero, which means that you go to infinitely strong coupling, this point goes to 0.25, or if you go to infinite weak coupling, you get to this value, so these lines will rejoin that dotted line here.
Yeah, so this second beta inside the graph then is
It's the beta function.
No, I'm sorry. You don't see beta functions here anywhere. Sorry, sorry.
The couplings of the
I should put here, I shouldn't call this beta or something. I mean, later I actually switched to beta L here to make a distinction. This is so-called lattice gauge coupling beta. I mean, it's just a very standard notation for it. Unfortunately, it's the same letter as in beta function, so this is confusion is guaranteed here. But this is a bare lattice coupling, and this G here is bare lattice coupling also. I mean, which has nothing to do with continuum gauge coupling. We will return to continuum gauge coupling and continuum beta function here.
The beta equals 0 there, meaning the coupling goes to infinity, and
yes.
So you call this the theory which is with infinite coupling.
Infinite coupling.
Which doesn't have anything to do with the way the beta...
Yeah, nothing to do with continuum. Infinite coupling is a lattice kind of artifact. On a lattice you can go to infinite coupling, strong coupling, and you can solve it analytically, the theory, as in the zero coupling too. I mean, when you have a weak coupling. Infinite coupling you cannot do anything in continuum theory, but on a lattice you can. Okay.
So why is beta equal infinity there
That's where this black line goes to.
This is where this goes to. I mean, when you go to infinity far away, yes. Okay. This is, I mean, QCD has very similar looking diagram. It's qualitatively completely similar, some on different location only, so that this is just fine-tuned. Okay, to be more precise, it's not quite that simple. This is not really crucial for any point here, but it turns out, when you look at it closer, that this zero quark mass line you cannot reach from this non-zero quark mass line, because suddenly there's a phase transition. When you try to make quarks lighter, there's a first order phase transition along this line where you jump suddenly to unphysical phase. So you cannot reach even the zero quark mass line there at these values of beta. But then there seems to be some kind of endpoint after which you can reach the zero quark mass line. That's around beta. Now I put here beta L, which is, I mean, just to separate it from the beta function. This is the lattice gauge coupling. I mean that after which you can go. This is not, also this is not new or unique for this theory. This is also has been recently seen in QCD for Wilson fermions. So this is a lattice artifact. Okay. So you have to be working on this line, on this side. It just means that your coupling is too strong, lattice artifacts are too strong, I mean, so that you cannot go there to zero coordinates. But here you can, at large enough beta. If this were asymptotically free theory like QCD, it would just mean that you have to go to small enough lattice space. In this case, because we don't really know how if this is asymptotically free or not, or something else, I mean, I cannot directly assign lattice spacing to these values of beta L, like in QCD. This first order transition is clearly visible, for example, in the placket, which is proportional to the field strength F mu nu squared. I mean, it clearly has a discontinuity at this critical line, and at that jump, the quark mass is still non-zero. Whereas at larger beta, meaning that in QCD this would be smaller lattice spacing, everything looks very smooth. So I have these 5 betas, their lattice gauge couplings, and I can measure this axial word identity. Again, I have this T here. This is in a way kind of this is a correlation function. Yeah, it should be AP, not SP, as I had before. So this is axial pseudoscalar current, and this is a pseudoscalar current. This BP. And by using that, I can measure the quark mass. Here is the measurement, and here is this bare parameter kappa. And for these 5 different values of this beta L lattice gauge coupling, at very large betas, I can clearly locate where this goes to 0, whereas on these smaller beta, I cannot go quite to quark mass because the first of the transition comes here and prevents me. It actually jumps to negative, but these volumes here are too large that I cannot even go there. I mean, technically, it seems to be too difficult, so that I cannot reach the 0 quark mass limit. Okay, this is all technicalities here. From now on, I will talk about only this measured quark mass. I mean, not the lattice parameters. I mean, it's much clearer when you express everything in physical units as you can. And let us look at the first particle spectrum. We have made 2 kind of studies of this theory. First, we looked at particle spectrum, which I'm going to describe here, and later we looked at this evolution of the coupling constant. First, for SU2 gauge fields plus fundamental representation quarks, like in QCD, I mean, there we would have 2 quark states, baryons, and quark antiquark states, kind of mesons, in the hadron spectrum. And these actually are degenerate in this case, except in isoscalar channel, because then this quark and antiquark can annihilate and mixes with blue balls. But otherwise those are degenerate, and then we have blue balls. Now, if we have adjoint quarks, adjoint representation quarks, we still have these 2 quark states, but it's possible also to have 3 quark states, which are almost like QCD baryons, I mean like proton, because the spin and etc. assignment is exactly the same and the symmetries are exactly the same as a proton or neutron. And in this case it's also possible to have quark-gluon bound states, at least superficially, because it's an adjoint representation quarks, and gluons have adjoint representation, so you can combine them to have color neutral states. Actually, in principle, you can form color neutral states by combining 2 or more quarks or antiquarks or gluons. I mean, no, take any number as long as it is larger than 2, you can have color neutral states in this term. We tried to measure this guy, we're not able to do it. It seems to be very, very noisy, very, very messy. I mean, technical reasons it's very difficult. But these we could access, and these we could also access easily. Globals are always very difficult to measure.
With SU3, so QCD, should you also be able to have 2 quark and 1 gluon states, which are color neutral?
SU3 2 quark. Yeah,
Which are not observed.
2 quark, 1 gluon. Yes, you should. Yes.
Does one know why they are not stable?
In principle, of course, when you have 2 quarks, like in a mesonon, you have lots of glue around it, so that you don't know.
Yeah.
But in principle, these 2 quarks could be in color adjoint state, adjoint color states, and then there's a third quark. So I think that, I mean, it's in a way it's not kind of the stable state, because you can, I mean, you can flip the spins and whatnot with the gluons and the quarks, and it kind of mixes completely with the mesons.
And are the glue balls observed on the lattice as kind of long-lived states?
Yes, they are. Well, I mean, they are very heavy and typically very wide, so they decay very quickly.
Okay.
But people have measured them. They are very difficult to measure. That's why we didn't even try to do it here. I mean, why not try to make your life more difficult? But this, of course, I mean, this you cannot convert into any 2 quark state, because I mean, you have only 1 quark there. So in principle, it's a stable state, unless it's so heavy that you can generate quark-antiquark pair, because these are massless.
Yeah.
I mean, it's in principle heavy, easy to have a pair generation there. But okay, what to expect from the particle spectrum? If we have QCD like chiral symmetry breaking, then when the quark mass goes to 0, then the pions are the Goldstone bosons. Their masses should go like quark mass square root of the quark mass. It's very, very funny, but this is kind of very generic, I mean, Goldstone mass behavior when you have chiral symmetry breaking. The quark mass is a kind of field which breaks the chiral symmetry, tilts your Mexican hat potential. When it goes to 0, you level it, so you restore the symmetry. And the Goldstone mode has a mass which behaves like the square root of this tilt. So that's why the pion mass is proportional to square root of the quark mass. Whereas the other particles should have a finite mass, even at the 0 quark mass limit, when you have a chiral symmetry breaking. However, if you don't have chiral symmetry breaking, for example, if you have a conformal point, this fixed point, then when the quark mass goes to 0, all states should become massless. Now, if we have a walking coupling, then of course, I mean, it probably would be very close loop, very much alike this conformal point, at least at higher energy scales where we are not yet kind of at the conformal, but at very low energies, again, we should see this chiral symmetry breaking rise. But they might be so far apart, these high energy, low energy branches, that you cannot really easily observe them on the left. Okay, you have always normal lattice problems, of course, finite volume and lattice spaces. But the results for the pseudoscalar, which is the Goldstone mode, and the vector meson, which is the row. I mean, this is in quotation marks because this is of course not really pi row, but I mean they have the same spin assignment as the pi row. At small beta, we seem to observe, here's the quark mass, the measured quark mass, and here's the measured pion mass. It seems to very much obey the square root-like behavior. So it looks like the chiral symmetry break. However, this is only at values where we cannot go to zero coordinates because of this first order transition. I mean, so that it is questionable, I mean, if there's any zero coordinates physics there. Here, when we go to larger values, these seem to go to zero, even though it's very hard to read from here. I mean, the data is not terribly good, but I mean, this seems to go much kind of with the non-zero intercept to zero kind of linear behavior there. Those green and blue points. When we look at the row meson, now at small beta, this seems to have a finite intercept. Doesn't go to zero with the square root like there, the dotted line there was a fitting square root. This has a finite intercept, which is exactly like in a chiral symmetry it should have, like in QCD. However, again at larger beta, we drop off this and it seems to go linearly towards zero. So
at these points on the negative mass side.
Yes. Yeah, I mean this is the kind of the unphysical branch, and you should kind of take them away. I just put it there because one can measure it, and you'll see that it bounces up, but it has nothing to do with continuum physics.
This problem that you said that for beta smaller than 2, you didn't hit the
zero.
The zero. How does one see it in this plot?
Well, you cannot go, I mean this white point, the last one, at this particular value you could get very close to zero, but for example on this black point the smallest quark mass is here, because if you try to get down here it just, you have this transition and it becomes actually impossible to do any calculus. Same thing with the red one, the last red point is there, so that it seems to fall on this line, but I mean you cannot just go there. And I actually kind of don't, I mean, in a way you should kind of, I think that you should kind of just forget that. I mean, it's a misleading result in a way that continuum physics is not there. I mean, because you cannot even go to zero coordinates on those values. But when you go beyond this value 2, then you seem to go linearly towards zero. Even though the data is not really as good. Same thing with this 3-quark state, which we call here proton, because it has the same symmetries as the proton. Again, I mean, you have a finite intercept at 0 quark mass at the small values, but then it goes to 0 at larger p. And if I take mass ratios, for example, pion over rho, it seems to be very close to unity at these larger values of the lattice beta, which would indicate that, I mean, it's kind of almost free quarks, or this kind of conformal behavior in this theory. Same thing with the proton, where the value now is 1.5, because other one has 3 quarks, other one 2 quarks. However, this comes with a big reservation, because if we look at fundamental representation, I could show the same plots, and they look practically identical. Even though we know that we have normal chiral symmetry breaking now here, no problem. Here we also are close to unity when beta is very large at the pi over rho. It also looks massless at large beta when the quark mass goes to 0 and we extrapolate there. Oh, sorry, this was the SU2 adjoint, and this is the fundamental. Sorry, yes. that was actually what I showed before. This is the fundamental. We have only two betas here, so that the small beta has this chiral symmetry breaking. Pions become light, so this mass ratio pion over rho becomes 0. But at large beta, it seems to hover close to 1 and drop only at very close to that point. So I mean, this looks kind of that both pion and rho goes towards 0. Whereas we know that that cannot be the case in this fundamental case. The explanation is here that in this case, when beta is 2.5, the lattice spacing is tiny and the volume is small. It's much smaller than the hadron size. You are effectively looking at the asymptotically free end of the QCD fundamental quarks, so that you don't yet see the quark masses. I mean, you are just too small volume. I mean, the quarks are still free. You have to go to longer distances. But it would mean that you have to go to extremely large volumes, and you would see this bending down only at very small MQA, because A is very small number. MQA has to, I mean, if MQ is fixed, I mean, to some physical value, MQA then has to be very small, I mean, or A is small, so that you would see this bending down happening at smaller and smaller values of MQA when you go to larger betas, even when you have chiral symmetry break. So that the spectrum might look like that. You will get kind of massless state that everything extrapolates towards 0, but it might be a finite volume artifact too. That was the outcome of the spectrum study in a one sentence. So in fundamental representation, let me recap. We know that there is chiral symmetry breaking, and we observe it at small lattice coupling, but at large lattice coupling, the lattice spacing is small, lattice spacing is smaller than hadron size, thus the system looks like that there is no chiral symmetry breaking, even to when we would make the volume bigger and bigger and the resolution higher and higher, we would see it finally into end horizon, because that's the physics. And this is all a finite resolution issue. In adjoint representation, we observe almost similar behavior. We can say that it is compatible with the conformal behavior at large beta small coupling. But it could be also finite volume resolution issue as here in fundamental representation. And the mass spectrum is not really sufficient to tell this. I mean, it's clear. At least it doesn't conflict with the conformal point. And you really have to turn to direct evaluation of the beta function. Oops, I'm spending too much time. I now tell a couple of slides of this direct evaluation of the beta function, which is really then which tells these things apart. And what we use is a Schrödinger, so-called Schrödinger functional, very clever method, originated by Lüscher et al. In the 90s, where the coupling is directly measured on the lattice by looking at the response to a background field. In this method, we generate a background chromoelectric field using non-trivial boundary conditions. So here is our lattice. At time equals 0, we put one special fixed boundary condition, and at the final time equals t, another fixed boundary condition, so that classically there is an electric field. It's simple enough to do, but so that if you solve the equation of motion, you will have a constant electric field through the system. You can calculate this classical action of this electric field. No problem, it's just solving the equations of motion and integrate it over the box. You calculate its action, and the action will be some number, which depends on the lattice geometry, and also of this. This is parameterized by some angle eta, these fixed boundaries. It depends also on this parameter eta over g squared. And we can calculate this classical action over the derivative of the classical action over this parameter, and it's some known number over g squared, where g is the gauge coupling of the classical theory. This is all. I mean, it would take, let's say, a couple of blackboards one blackboard to write, but I don't go into technicalities. It's just follows directly from the classical action of the QCD or QED for that matter. Now, we now use this to define the coupling. Just invert this at the quantum level. We define that 1 over g squared is 1 over this a, where a was the known constant here, times ds over dE, the derivative of the action with respect to this parameter with parameterizes this with fixed boundaries. And this boils down to be some constant times the expectation value of the boundary brackets of this theory, which is a directly measurable quantity from this simulation. So the calculation is done so that we fix the boundaries to these special values and we measure this boundary bracket expectation value multiplied by the known constant, and we get 1 over coupling constant squared. And this method evaluates the coupling constant at length scale L, the box size. So it's not the lattice, I mean bare lattice coupling constant, it's really the long range coupling constant on the lattice. And this method has been used very successfully in QCD by Alpha collaboration through 90s. They had a series of close to 10 papers about this, where they formulate the theory. All in all, I guess something like 300-400 pages when you all stack them together, and the result is in the particle data booklet. I mean, the determination of the QCD coupling from the lattice simulation and the evolution of it. They calculate the evolution from QCD scale to electroweak scale using this method. So now we use the same method in this theory. I skip all of the technicalities, but first we do measure this g squared. Now g squared is an observable, measurable. This is the g squared at the box, evaluated at the box size L at different lattice couplings beta L and different lattice volumes. And first here we test with fundamental representation, where we know that we have asymptotic freedom. And for example, if we pick one particular lattice coupling here, let's say I look at this red point 2.8 here, one box size 4, 8, 16, we see that this increases as I increase L, which is true. I mean, when you increase length scale, the coupling constant in QCD should increase. So if I would continue here, it would increase further and further. This continuous line is a coupling evaluated from perturbative two-loop beta function, which is known, of course, in this theory, and it matches very nicely to these points, except here at the smallest volume, where the volume is so small that lattice artifacts start to play. You get different curves when you use different bare lattice coupling constants. How should you relate this? I mean, why do you have a family of curves here? It just means that the normalization, I should put here actually L over A, L over the lattice spacing. These have a different lattice spacing. All of these red points have the same lattice spacing, so that this point at 4 is half of the size as the point at 8. But it's not directly, the size relation between these red and green points is not directly known. I mean, you should kind of move these curves sideways until they match and form kind of continuous line. Then you would kind of know the evolution of the coupling constant over this whole range. I mean, so in this way, using different bare lattice couplings, we kind of get a sample of the evolution of the coupling constant in one range, specific range. And we could patch these together. Let's say I would move this curve here horizontally sideways until kind of this hits that. I should actually not move it with kind of as a constant, but multiply it by suitable factors because there's a multiplicative unknown factor. So if I would multiply the x value of these points so that this meets this line, then I mean they would kind of join together, and I would know that I mean the lattice spacing here is, say, 3 times larger than the lattice spacing here. But here they are in lattice units, so that you have the different curves. But all of this agrees with the asymptotic freedom. I mean coupling increases as you go to larger system sizes, and the bigger the coupling is originally the g squared, the faster it increases. It actually should somehow even diverge at some value when you reach the proton size or the baryon size. Now, this adjoint theory, it looks completely different. I have here much more points, and here, well, I mean, it basically doesn't evolve at all, extremely slowly at very small couplings. But at larger couplings, it first increases and then it starts to decrease, especially this point here. And okay, the small volumes, one can say that these are affected still by lattice artifacts. The larger the L over A is, the farther you are from the lattice cutoff, so that you kind of have to drop the points there. And if I drop the points all which are below 10, these ones, I see that this goes down when L increases. These actually go up. You cannot see it here. The resolution of the plot is too small, but indeed these go up and these go down. And the fact that these go down as L increases means that the beta function has a different sign. It actually has a positive sign. Coupling becomes weaker as you go to longer distances. And these seem to converge. I mean, you can assume, well, these data points of course don't tell you it really with kind of completely without, I mean, there are interpretation issues, but if you take the minimalist approach that these go down and these go up, they will converge then at some point, and that would be this particular value of the coupling, the fixed point of the coupling. So at small beta L we have large GL, and G decreases as L increases. And when L goes to infinity, in all cases the GL apparently flows towards a fixed point, which is not determined very well. The G squared is between, of this fixed point value, between 2 and 3 here. If this is the case, this would indicate that this theory has a conformal behavior. And okay, these continuous lines here are again, I mean, a beta function. We have made the beta function ansatz fit to the points, and then evaluated through that so that it's consistent with the beta function, which show this behavior. And the beta function is shown here, which doesn't show very clearly. We describe with the function with an ansatz like this. We have two first coefficients which are directly from perturbation theory, g to the 3, g to power 3 and g to power 5, but then we put a kind of remainder term with two constants, the multiplicative constant b3 here, and the power delta. I mean, why delta, why not 7 there, but we just wanted to have it more degrees of freedom at larger coupling so that it can kind of cover more phase space. And let those vary. So we fit this beta 3 and delta to the data, what was there before, and obtain a beta function which looks like this red line here. So this is the asymptotically freed part of it. One loop perturbation theory goes here, two loop perturbation theory. Two loop perturbation theory actually does have a fixed point around this G here already, so that was kind of known, but people didn't know how reliable it is, but this data seems to indicate that that the true fixed point is a much smaller coupling than the two-loop prediction theorem gives you. However, there's a lot of uncertainty here. This band here is kind of more or less the uncertainty band around that solution. But this is kind of the direct evaluation of it. Now you can integrate the beta function. Beta function is the derivative of the coupling. You integrate it, you get the coupling as a function of energy scale. And that's this red line here. And if I start from a weak coupling at some particular value and then go down in energy, the coupling increases like in QCD, but instead of diverging, it reaches this fixed point and then approaches it when I go towards the infinitely small energies. And at this value, the theory is conformal, scale invariant, of course. The coupling constant has another branch here at the other side of the fixed point, which is true, I mean, in reality completely disconnected. So you cannot really compare the energy values here because you cannot go from here to here by adjusting energy. I mean, because this already covers an infinite energy range. So that these are completely disconnected.
Is this a different theory which has different interactions?
I mean, in principle, they are the same theory, of same Lagrangian, same interactions. And here, of course, if you are here or here, you cannot really tell them apart by looking at interactions. It's only by kind of changing the scale a lot you can see that, oh, this goes up and this goes down. I mean, it's the property of the fixed point. I mean, it's yeah. Yes. At the infrared, all of these, of course, look the same, so that the infrared end is similar. Well, these curves have very large error bands, actually, so that for clarity, not shown here, so it's not very well determined. I mean, the location of this can go up and down here, but I mean, the fixed point seems to be there.
How long does it take you to make these plots?
Well, the simulations here took something like, I don't know, 4 months, 5 months.
All of them, or just for one value of beta n?
Well, each pound takes like...
Sorry? Each?
For 1 pound, it takes like a week or...
Yeah, well, I mean, okay, I mean, this is where the results are. These are the results and the measurements, and I have to say that, okay, these points you get very easily. You can calculate almost on your laptop. When you go to here, I mean, these points here, you have to calculate on a big supercomputer, and I think that, for example, the points at this corner, I mean, each of these individual points took on a parallel computer, I mean, CPU months, so that with using 1,000 processors, so that it's for individual CPUs, you should calculate tens of CPU years for those points there. But these are then again really easy, so it's a trade-off there.
And if you have L over A 20, this means you have a 20 to the 4 lattice.
Yes, 20 to the 4. Yeah, it's symmetric lattice, 20 to the 4. It's not particularly big, but you have to calculate quite long time. This is a noisy measurement, and you really have to kind of get lots of statistics, and as you can see at this point actually doesn't mean anything because the error bands are so large, but we just decided that this is enough. We cannot go further. The conclusions very largely are based on these 3 points, I mean, and that these go down. And if you don't believe that, there's something fishy here about this point, so that you should exclude this, then I mean, a whole thing collapses like a card house or something, because then you cannot say that this really goes down when you go to larger L. So that the existence of this infrared fixed point is really based on the fact that these points go down as L increases, which is completely opposite to normal asymptotically free behavior. I'm not worried about this, that this goes up and then down. You might be worried that is this then along this line yet, I mean, or that there should be a deviation here too. I mean, these kind of have to go down because there's a at L equals 1 I can calculate where it should intersect, and they are at much smaller values here, so that the lattice artifacts start to bite you there. And you should do this, we should do this with improved action, which should help the behavior at small volumes, so that I would hope that this would then get up here with an improved lattice action, which is not so sensitive to this lattice kind of thing. But this is one of the first determinations of this infrared fixed point, non-trivial infrared fixed point in a lattice theory. And well, for this particular theory, this indicates that, okay, there seems to be an infrared fixed point, which means that there's no chiral symmetry breaking, there's no walking in this theory per se. I mean, it just hits this infrared fixed point when you go to infrared, and that's it, stays there. Now, you might ask that as a technical theory, I mean, is it still viable? Can you deform it somehow so that you would recover a walking behavior? A very simple way to do it is just to put a small quark mass. Because when the energies are much larger than the quark mass, it's irrelevant, you are still, I mean, flowing towards this infrared fixed point. But when you go lower and lower in energy, suddenly you reach the quark mass. And when you go to lower energies, the quarks are heavy, and they decouple heavy quarks from your system. So you are in a pure gauge SU2, which is confining, and suddenly you kind of drop. So if you have a finite quark mass, you would get the walking behavior like that, and the coupling constant would then look like presumably look like this. You go up here, approach this fixed point value like here, but suddenly when you reach, this is now your energy scale mu, this is your quark mass mq. When you reach mq, the quarks become heavy and they go out. Their effect on the beta function drops, so beta function becomes steeper, and you suddenly then start to increase again. You have a walking behavior there. So it would modify this so that, well, if you would continue here, and this would go up at the scale where the quark mass is. As you see, the scale here, range of scales here is 40 orders of magnitude, so you really have to run. It evolves extremely slowly. You're already away from the fixed point. The coupling is much lower than in QCD. This leads to confinement and possibly to chiral symmetry breaking. It's not clear to me completely because you have very heavy quarks now. Obviously, when you go to lower energies in the quark mass, you can follow that chiral symmetry breaking, but at least you go to stronger couple. Now, this is, of course, you shouldn't add the quark mass to technical because this is completely against the spirit of the technical theory. I mean, mass terms arise in standard model through Higgs, and now you use technicolor to get rid of the Higgs, and now you add mass terms. So this is a very circular way of doing it. So you should argue that something similar happens when you couple this theory to standard model or this extended technicolor, which is the higher order theory. We don't know. I don't know yet whether or not something like this could happen. Okay, but there's a lot of work to be done using improved Fermions that is going on, using this investigate walking maybe with MQ, finite temperature phase transition, which is relevant for electroweak phase transition, of course. Using different groups, different representations, which are also candidates for this. And in principle, I mean, if you can make this work, I mean, if you can have a chiral symmetry breaking and walking like this, you can get really concrete predictions from this theory. For example, I mean, you can measure the quark antiquark condensate and set it to Higgs expectation value 246 MeV, that sets the scale, and now you can attempt to measure the scalar mass, which is the Higgs mass then, so that this gives you deterministic Higgs mass, if
So-
you can make it work.
You said you don't have electroweak symmetry break.
Yeah, I don't have, but I mean, if you manage to cook it so that you have a symmetry break in it. In this particular setup, we didn't have it. But if you have a different theory, or you manage to modify this somehow, that
So you
get-
contradict the prediction by Francesco Salino? I'm a bit confused. So essentially you're saying that you cannot have electroweak symmetry breaking in this.
Yeah, I mean, I think you and Francesco, you had this effective theory and you adjusted the parameters.
So-
I mean,
You mean, well, so we just assumed that it was working. But,
Yes.
You were assuming it was
Yes.
working.
But, well, if it's not, then you have to couple it to something instead.
yes. So it's
But this is not published yet, right?
And
This
it
is,
is. It is.
it is?
Yes.
It is recent.
It's recent, very recent, yes.
One thing is that this effective field theory is not too much dependent on the underlying theory, so it's a rather general model of this kind of theories.
That's right. Yeah, the problem with this lattice stuff is that I mean it takes a huge effort and lots of
So
manpower
what is
to.
Francesco trying
one
now to
result.
make it work?
Well, I'm not sure if Francisco is yet convinced that it's not working. But maybe but he also has other candidates that work. Then he
Well,
will
but
always-
in these other candidates, he's also making assumptions. No?
Yeah, so you don't know if they're working or not.
No.
But somehow, I mean, to me, it might be easy somehow to get a working behavior. Right? It depends if you can introduce a scale. If you can introduce a scale to your theory, maybe through some kind of seesaw type mechanism, which is a kind of small enough scale arising maybe at some higher limits in physics, which acts exactly like the coordinates. When you have a scale there, you can argue that above the scale you have one behavior and below that scale you have another behavior. Thus you could have a walking type physics like the coordinates gives you here. But automatically it can be, yeah, I mean it can be any coordinates and that clearly destroys the infrared fixed point. Infrared fixed point can exist only at zero coordinates. If it is any
But is
coordinates,
there a way
you
to
don't
make it
have-
work without adding any mass then?
Sorry? Yes.
So can you make this work without
Yeah,
adding
that's a
mass?
good point. I mean, this ETC gives you this kind of 4 Fermi couplings, which, I mean, they might be like coordinates. I mean, it's also for the technical.
Mm.
The fact of making this at finite temperature does not play any role in this problem.
You should have a zero temperature chiral symmetry breaking. Then you can look at the symmetry restoration at finite temperature first.
Yes.
But yeah, indeed, I mean, you can get a prediction of the Higgs mass, you can get a prediction of these exotic particles when you have this kind of walking behavior set in here. But of course, these are all modified by this extended technical corrections, which we didn't include, and I said too much there, which modify some. But walking behavior
what
is,
is your plan now? Are you
well, first even to observe this kind of infrared fixed point is kind of important step, because those are not common in field theories and very little is known about them. So we want to do better job. We want to use improved fermions over and do a very careful job. I mean, try to characterize it is better. I mean, many people criticize us for the using non-improved fermions because they can have large cutoff effects, but this is the minimalistic approach. At the first we want to do everything as simple as possible, so that the least amount of tuning and fiddling around. And then, I mean, it all hinges on these few points here. So you would have to somehow really hammer down the behavior here in order to have a convincing case. But it is not completely alone. I mean, also the SU3 with actually, sorry, two index symmetric quarks, the Grant et al. Have seen indications of this behavior. Although privately they tell me now that when they switch their action to a new one which is maybe too improved, or then they don't see it anymore. So it's a very non-trivial issue, and I think it takes still some time to make a really clear case what is going on. But I'm reasonably happy with this, and I'm kind of convinced enough to claim that this has a non-trivial fixed point. This theory. And indeed, using the improved permanence is on program for this year. And then we want to investigate what happens when you look at do the same stuff with the small quark mass, so that you would get the walking behavior to you get with the quark mass, which is the minimal modification. It's already included in the theorem, and we can do it at any quark mass. So that do we get kind of electroweak symmetry breaking then in this case? Okay, yeah, thanks for your